All right. If we look through these problems that we are given in this packet, we see we're given all these functions that are all capitalized. We got this big R here. In the next problem, we have capital A. We got capital G, capital W, F. And we think, oh, those are, functions. Those are, possible antiderivatives, which we're used to with capital letters. But if you read the question, it says that each one of those functions are rates. Like the first one, R of t is the rate at which water is flowing into a drain pipe. If you go to D, D is the rate at which water is allowed to drain out the other end of the pipe. We look at G. We kind of dealt with this problem last time. The rate at which unprocessed gravel arrives at a gravel processing plant. We look at W. We are told W is the rate at which water is pumped into a tank. When we think of rates, we think of those being derivatives. Rates of change with respect to t would be like a derivative. We're used to dy dx, but these would be derivatives with respect to t of some function. Okay? So even though they're capitalized, they could be thought of as derivatives. Well, if we understand that these are rates / derivatives, we can think about what their antiderivatives would be. So like if I have R of t, the rate at which rainwater flows into the pipe, and I took the antiderivative of R of t, maybe don't give me a letter, but tell me what it would mean. It would be a total amount, yes. So if you think about it, it would be the total amount, some function that would give the total amount of rainwater that has flowed into the pipe. Right? Well then D, if I took the antiderivative of D, we'd see that would be the total amount of water that flowed out of the pipe. Okay, if we have G, the rate at which gravel arrives at a processing plant, well, the antiderivative of G would be the total amount of gravel that has arrived. Okay, et cetera, et cetera. Rate at which water is pumped into a tank. The antiderivative of W would give me some function that would give me the total water pumped in. Rate at which traffic flows through the intersection. The antiderivative would be some function that would be the total traffic that has passed through the intersection. Okay. Now it's important you know that they aren't going to give you a letter to use because they're already starting with capital R, capital D, capital G. But what we're going to probably want to do is say that this is equal to some total. And we'll use some other letter to define it as the antiderivative of what I'm given. So I like to use T. You can use whatever you want. But it's nice to say, okay, T of T, its derivative would be R of T. If I have the total amount of water in the pipe that has flowed into the pipe at a given time, its derivative would be R of T, the rate that the water is flowing into the pipe. Okay? And you can use any variable you want. If you have rate at which water is flowing out of the pipe, you can go O of T is the total amount of water out of the pipe. Rate of which gravel is arriving, I don't know, A of T could be the total amount of water that has arrived. And the important thing is that the relationship between T and R, O and D, A and G, yes, the antiderivative of this, but the derivative of T would be R. The derivative of O would be D, et cetera, et cetera. Does that make sense so far? It's really interesting how they do that. They don't tell you that it is a derivative. They give you a capital letter, mostly to try to trick you. However, typically, though, we will be unable to find the antiderivative of the rate, or they won't give us initial condition to find C. So you will see in the problems, R of t is 20 sine of t squared over 20. Can't take the antiderivative of that. I could take the antiderivative of this if I wanted to give me a function that would model the total amount of water that drained out of the pipe. However, I don't have an initial condition for this antiderivative. I don't know that at time 0, this amount has drained out of the pipe. We can assume it's 0, but maybe it's something else. So I don't have this C to help me find C. If I look at some other ones, this is the gravel. I'm not going to be able to take the antiderivative of this. W, you'll see, is 2000 e to the t squared over 20. Not going to be able to take the antiderivative of that. Not going to be able to, can take the antiderivative of this, but maybe I don't have an initial condition. So instead of finding the specific antiderivative, we're going to use the fundamental theorem of calculus to find the change. So instead of just finding the antiderivative, we will say, hey, what's the antiderivative from 0 to 5? And that's something that I can calculate. This will be the total change or the total volume of the water that flowed into the pipe from 0 to 5. Okay, it's the change in the antiderivative. So instead of how much water flowed out of the pipe getting a function, I'll say, hey, what's the change in the amount of water that flowed out of the pipe by finding the area underneath that. So I'm going to find the area from A to B of a rate, and it would get me the change in the total. Okay? Now, if they're going to want to ask you, hey, how much do we have or how much is flown out, we could say, hey, our total amount at some future time will equal a total amount at my initial time plus my change in my total. Well, that's the area from A to B of my rate. dt. Okay. Now there's some specific things that we're going to be asked, some guidelines for these rate problems. I've already told you, use a different function to represent the total. Here's an example. It's the first problem that we're going to do. Given a rate that water flows into a container is R of t, and the rate that water flows out of the container is P of t. They use different ones. An initial amount of water of 10 gallons. I would say, okay, well, the total amount in my container will be represented by T. Now, if you think about it, T prime would be the change in the rate at which water is coming in, or the change in the rate of my total amount, not necessarily just coming in. In this situation, we have a rate at which water is coming in and a rate at which water is going out. In this situation, if I wanted to say, oh, this is the total amount that flowed in, we would say T prime is R. But if I say, oh, this is the total amount that it flowed out, then we would say T prime is P. But if we're just talking about the total amount of water in the container, what would T prime be? What do you think? So the rate at which it flows into container. However, there's water flowing out of the container as well. The difference between the two is exactly right. In this situation, if we're talking about T being the total amount in the container, the change in T would be the rate at which water's coming in minus the rate at which it's going out. So all of a sudden, if we took the antiderivative of this minus this, I would get the total. Does that make sense? We got stuff coming in, we got stuff coming out. If this is the total amount of water, well, the change would be that. Yeah? Okay. So that's important. Well, I can use the application of the fundamental theorem of calculus to find values. I could say, hey, the total amount of water at time 5 will equal my initial amount of water, which is 10, plus the change in my total amount, which would be the area under T prime, with T prime being R minus P. And frequently you will be asked to find the max and the mins of a total amount. So this is when we go and remember optimization, absolute maxes and mins. To answer when you have a max or min, you need to recall and you need to check, and it's the whole candidates thing, locations of your relative maxes and mins and your endpoints. So relative maxes and mins are going to be when T prime changes sign. In this situation, T prime would be R minus P when that changes sign or when that equals 0, or the endpoints. Okay? That's it. Now let's do some rate problems. Whatever we don't get to is your homework. We got 30 minutes. I feel like we can get like 4 of these done. No, that's ambitious. Let's go for 3. All right, here we go. The rate at which water flows into a drain pipe is modeled by R, where R of T is 20 sine T squared over 35. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by that, cubic feet per hour, for 0 to 8. There are 30 cubic feet of water in the pipe, starting at time 0. Part A, how many cubic feet of rainwater flow into the pipe during the 8-hour time interval? Go. You'll need a calculator. Make sure you're in reading mode. So it's not, it's just how much that is flowed in. It's not like a total amount. So the initial amount that they give me, I don't need. That's it. We should get just 76.57 gallons. No, cubic feet. Sometimes. Usually they will say specify units, specifying units, blah, blah, blah. But here they say how many cubic feet. So you just do a numerical answer, and they already told you. Okay? R of T is the rate at which water is coming in. So the antiderivative would give me the total amount that has come in at a specific time, but can't find the antiderivative of that. So if I find the area under R of T, it'll be the change in the amount of water that came in, and that gives me the total flow of water from 0 to 8. $76.57. Okay. B is the amount of water in the pipe increasing or decreasing at time t equals 3. Give a reason for your answer. Go. Discuss with your neighbors what you should be doing. If you're struggling, all we need is increasing or decreasing, and at what rate you can find. I say it's decreasing. Anybody else say it's decreasing? Yeah? Can we discover how much it's decreasing? $3.3 is what I got. Okay, how do we get this? Who did it? Tell me. Mr. Quigley? And what am I looking at when I get my answer? That's all right. That's right. So if it's positive, what's that tell me? Right. And if it's negative, Okay, so good. I like what Mr. Quigley did. You didn't have to do that. You could have just plugged in 5 into this to find the rate at which water's coming in. Okay? If the rate at which water's coming in is larger than the rate at which the water's coming out, well, then you know you're adding water. Yeah. Oh, why did I plug in 5? Sorry. Hold on, go back. Did I still get it right? So the rate at which water is coming in is 5.086. The rate at which water is going out is 5.4. So it's decreasing. Okay, good. But by just very close to each other, just 0.313. You got that, Mr. Ramanetti, 0.313? Okay, good. So what Mr. Quigley did, he says, okay, well, the total, let's just say is T. The total water in the pipe. He said, well, T prime is going to be R minus D. If T prime is positive, water is increasing. Right? The derivative is positive, we're increasing. If T prime is negative, water is decreasing. Okay? So all we have to do is plug in T prime of 5. If it's positive, we're increasing. If it's negative, we're decreasing. Okay? Part C. At what time is the amount of water in the pipe at a minimum? Go. We got to think, okay, I want a minimum for the total amount of water. That's going to be at a relative min for T or at an endpoint. So I need to see when T prime changes sign from negative to positive. That'll be the location of a relative min. I also need to check 0 and 8 and compare. Unless we can figure out the signs of T prime and really specifically say that's definitely going to be the min. Robert Messner. Hi, how are you? So we are unable to solve this equation right here. So instead, we will use the power of our calculator to graph. So let's go ahead and plug that in. Now I have to subtract this entire thing. And it's really annoying that they gave you such a big function, but you got to deal with it. Okay? Graph. Turn off stat plot. Standard. Okay. This is looking promising to me. Okay? Extremely promising. Because when I see that, I'm thinking, sweet, most likely I don't have to worry about justification that much. And I don't have to check my endpoints. Do you see why I say that? T prime is negative until we get to this point. And then it's positive, super positive until probably past 8. If I go to 8. Right, good. That means between 0 and this time, we're going to be decreasing in the amount of water because T prime is negative. And then after that time, we are increasing. So if we just go decreasing, then increasing the entire time, that's got to be the location of my absolute min. Okay? So I don't have to check my endpoints as long as I state that. It's like, oh, T prime goes from negative to this value to positive, and it stays positive. This has to be the location of my absolute min. Now, how do I find that value where we change signs from a negative to a positive? Don't put your cursor over it and say that's good enough. Okay? Use y equals 0 and find the intersection. Go ahead and find that intersection. Second calc, intersect. Now, let's first make sure this is 0, 0. I believe it definitely is. I know it is. I pressed it too many times. Yeah, good. So that's 0, 0. That's great. Then we're going to decrease until this time. Too far. Boom. T equals 3.2716584. That will be the time when T prime changes sign from negative to positive. Yes?
What do we do after we plug in the y value?
We graph y equals 0 as well. Right? We there? And you got R minus D here. Okay? So we're going to go to second calc, and we go to intersect to find, the time when your y is 0. You go enter, 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 and it gives you the value. First curve, second curve, third curve. Are we comfortable with that? Okay? So, again, T prime went from negatives at that point to positives until 8. That is telling you that that's got to be the location of the absolute min. That's all they're asking for is the time. Now, typically, they will ask you as well, what is the amount? How could we find that?
Do the thing where you have the a point plus the antiderivative from that to the value.
Exactly. The application of the fundamental theorem of calculus. If I want to find the minimum value, we did exactly what we learned last lesson. What we learned last lesson is if I want to find my total amount at this time, I will use a given known value. Do I have a given value for the total amount of water in a pipe? What is it? 30, right? It was given in the question. We started with 30 cubic feet of water, okay? So I'll say that this is equal to T of 0, which is 30, plus the change in my total. Again, T being the total, the derivative would be R minus D. You can either do the antiderivative or the area from 0 to 3.27 of R, and then minus the antiderivative from, or the integral from 0 to 3.27 of D, or you can just do it all at the same time. It's up to you. I like to do it all at the same time, T prime, which is R minus D. Okay? And that's how you find the total. Now let's look at part D. Now in terms of the justification, this is not proper justification. You'd say You know, T prime is negative, like the water amount is decreasing until this time and increasing from there on. Therefore, that must be the absolute min. That's what I would kind of write down. Now, part D is the pipe can hold 50 cubic feet of water before overflowing. For T is greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. Write but do not solve an equation involving one or more integrals that gives the time W when the pipe will begin to overflow. Go. See if you can do that. So we have, when is the total amount going to be 50? Well, we'll have the initial amount, we'll have the change. This would be my answer. This would give you full credit. Okay, rate problems. They're kind of tricky. Yep. Sure, if you want to do that. But they said it still does this, right? So might as well just go from 0 to W, and you'll get that. Now, it's very important that sometimes you have to read the question carefully. I didn't like how I put this as number 2, but it's okay. Read the question. It says the amount of grass clippings remaining in the bin is modeled by A of T. Is capital A of T a rate? No. This is a total amount. This is not a derivative. This is a total. So that helps you. They ask you to find like A prime. Well, that'd be the rate of change of the amount of clippings. That would be kind of what we looked at in the previous problem. When is the amount of time equal to the average? We'll talk about averages next class. Don't worry about that. Linear approximations. We did linear approximations last class. Okay, so let's skip 2. Let's see if we can get through 3. Go. We kind of already started with this gravel problem last class. So let's see all of the parts that the AP test asked of students when this was a question. Yeah. Sure.
Number 1.
Uh-huh.
I plugged in the y value.
Minus. Yep. Okay. Yep.
And I
Graph.
graphed it. I don't know why, but I graphed it.
Oh, I just typed it in wrong. Oh, you're in degree mode. Yep.
Oh, okay.
Be in radian mode. Yeah, radian mode for calculus, degree mode for physics. Now, everybody know how to find derivatives quickly in your calculator? Math 8. Recall, Math 8. Math 8. The derivative of your function at a point. Find g prime of 5 by just plugging in this. Since it's a calculator question, you would probably have to write down that you're typing this in. In -24, g prime of 5. equal to d dx of g at x equals 5, which is negative 24. Yeah. So math 8, your function, comma, x, comma, the number. So just like with integrals, but instead of two numbers, you just have one number. Okay. So what does that mean? Interpret that. G is already a rate. We're finding the derivative of g. What does that mean? It's the rate at which the rate is changing. Literally. It's the derivative of a derivative. It's like the acceleration. The rate at which gravel is arriving at the plant is negative, which means, you know, you're decelerating in the amount of gravel that's arriving at the processing plant. Isn't that crazy? Right? But that's the question. It's like the acceleration. It's the second derivative. You could write it's technically like the acceleration of gravel entering the plant, or you would say it's the rate of g. The rate at which the rate of gravel is entering the plant, right? It's the derivative of the derivative. Total amounts of unprocessed gravel that arrives would be your integral from 0 to 8 of g of t. You'd find that. Is the amount of unprocessed gravel increasing or decreasing at time t equals 5? Well, we are processing gravel at 100. So if g of 5 is greater than 100, then we are increasing. If g of 5 is less than 100, we're decreasing. What's the maximum amount of unprocessed gravel? Again, let's start with a t, which is the total. T prime would be g, which is the rate at which gravel is entering, minus 100, which is the rate at which gravel is leaving. You'd plug g minus 100 into your calculator, see where we had a min, where it changes from negatives to positives. Then either confirm that that's got to be the location of the absolute max, sorry, when it changes from positive to negative, confirm that it's the absolute max, or you might have to check your endpoints if it's not clear that that's the absolute max, okay? All right, go to the pep rally, or stay here, I don't care. Finish the rest of these problems for homework. The answers will be online, but I'm probably going to put them up on Monday. So if you want to work on the weekend, work on it over the weekend, but then check your answers on Monday.